Hello. All right, so let's continue with our second part of persistent homology. Okay, so far we know we would be able to quantify the shape of a given point cloud or data in the form of Betti numbers. Yeah, so we have Betti numbers, we can compute Betti numbers, whereas we can also compute in the form of Euler characteristics. Right, so we can compute Euler characteristic for a given point cloud or a Betti number for a given point cloud. Of course, Betti 0, Betti 1, Betti 2. Yeah, but 0 is representing connected component, Betti 1 representing one-dimensional hole, yeah, one-dimensional hole, and Betti 2 representing two-dimensional hole. Okay, so this is an example of a torus. Normally, we do not get our data set in this form. Yeah, rather, we get data set with in the form of a collection of points, right? So it will be in this form actually. So using this collection of points, we need to compute Betti numbers. Also, we would be able, once we have Betti numbers, we also would be able to compute Euler characteristic for a given point cloud. Okay, so these two informations are basically the information of the shape of a point cloud, in which we can later on represent it in the form of a vector, or specifically a feature vector, which we can then use for machine learning. Okay, so now how to extract, given a point cloud, how would I be able to extract all this shape information, right? So your so-called your true shape is in this form, but however, you sample it out using some sort of observation or measurement, you get all these points that you compute, right? All these points. But the real true shape is in this form, right? Okay, so the idea from given point cloud to extract the shape information would involve the construction of simplicial complex. Okay, the construction of simplicial complex. It's simply, you can think of it as a triangulation of a given point cloud. So a generalized triangulation of a given point cloud, we can call it as constructing the simplicial complex. Okay, so the construction of simplicial complex is basically the creation of edges between the points, right? For example, and then also the creation of face, yeah, between the points, the creation of creation of edges, vertices. Oh, sorry, vertices are point clouds, edges and faces. It can be in any dimensional space actually. So for in a dimension 3, it will be tetrahedron. In dimension 2, it will be a triangle, and so on and so forth. Right. So of course, there are some rules. For example, every single edge, every single vertex would be your point cloud. Right. So these are your point cloud. You should not create an edge in between of edge. So for example, this is one edge, this is another edge. You cannot simply create connecting in the middle of the edge. Rather, you connect the vertices to create edges. And then when you have triangle, in three, when you want to create a face between 3 points, this is incomplete where one edge is missing. Yeah. So as you can see, one edge is missing. So it is also, you cannot do that, right? So again, you cannot go through the face of a given triangle also. So this is a face, you cannot go through. So these are some simple rules and regulation to create a proper simplicial complex. Okay, so an example. So you have a point cloud. This is at some resolution. We have collected the points. We have then create some. There are also some faces in there. As you can see, these are faces. Yeah. So we have edges. All these are original points, original sample observation in your point cloud. Okay, this is one point cloud. Okay, so after doing after constructing simplicial complex, only then we would be able to compute the information of the data, right? So for example, here, you see how many connected components. So for example, you want to compute Betty 0. At this resolution, we have 1, and then the rest is 1. So we have 2 connected components. So I would be able to compute Betty 0 as 2, right? Whereas how many holes are there? There are actually one hole, you can see here, one-dimensional hole, and there's another one-dimensional hole here. So we have Betty 1 as 2. How about Betty 2? This is only in two-dimensional space. There is actually no Betty 2, no tetrahedron here. So Betty 2 is 0. Okay. So this is an example how we compute. So if we were to calculate Euler characteristic for this given Euler simplicial complex, the Euler characteristic will be the alternating sum of Betty 0 minus Betty 1 plus Betty 2, which is 2 minus 2 is equals to 2 minus 2 equals to 0. Okay, so at this resolution, I kept saying at this resolution, I see some part are not connected yet. As you can see, some part are not connected yet. Yeah, for example, let me delete first. For example, these parts here, they are not connected yet because we have yet to reach to the resolution. Okay, so at this resolution, the Betty 0 is 2, Betty 1 is 2, and then Euler characteristic is 0. Okay, so now you can see that given a point cloud, we can construct simplicial complex, and then we can compute the shapes information. All right. So before we proceed further, let's understand a little bit on simplicial complex. Okay, so there's a zero simplex. Zero simplex is basically a point, and this point can be in any dimensional space. A point is still a point. It's just that it has many features, but it's still a point. In R2, for example, you have X and Y. This is a point. In R3, we can have X1, X2, X3. Similarly, in R10, you have X1 until X10. Right? So it's still a point, it's still a point. So it's called zero simplex. Okay, and we represent it with a bracket. Yeah, a bracket like that. A. So A is representing a sample or a point in your point cloud, in your data set. Right. Then we have one simplex. One simplex, we join 2 points with an edge. Yeah, this is one edge. This edge, you said we write it A, B. So A, B in one bracket, just like writing an interval A to B, right? So A to B. So, but in the form of vector, we can say B minus A, which means A goes to B, right? That's a vector. Okay, so A, B, actually it has got some sort of orientation, A, B, or B, A, right? So they are not the same actually, all right? They cannot be the same because there is some sort of orientation to this simplicial complex, one simplex, okay, an edge. The next thing is a two simplex. So the two simplex, as you can see now, it has a face, that's a filled triangle, whereas a three simplex, so the filled triangle is written, as you can see, A, B, and C with 3 points, 3 zero simplex. Okay, and then a 3 simplex is actually a solid tetrahedron. Yeah, a tetrahedron is just a triangle filled. There's a solid tetrahedron. Okay, filled. It's not hollow like a sphere or a ball. Okay, so a solid tetrahedron, you can see it's A, B, C, and D. Okay, this is a 3 simplex. Okay, now some people, students get confused between two simplex and one simplex. So the two simplex, remember, it has a filled triangle. This is a two simplex. Whereas one simplex, this is a collection of one simplices actually. 1, 2, 3. So 3 edges. 1, 2, 3 edges. A, C, C, B, B, A. So it's a collection. 3, 1 simplices. 3, 1 simplex. Okay. So plural, we say one simplicis. All right. And again, solid tetrahedron is not equal to sphere, because a sphere, it is a manifold which is Betty 2 equals to 1, whereas a solid tetrahedron Betty 2, this is actually filled, so there is no hole inside there. Okay, it's filled. Okay. All right, so there you go. So a little understanding of the building block of simplicial complex. Okay, so now one simplex, you have one simplicial and then two simplicial complex, right? And so now this is just one simplex of two simplex. Yeah, one of two simplex. This one is what we have three of one simplicis. Three, 1, 2, 3. Okay. So for here, of course, two simplex we have face, but for one we don't have. Okay, it's covered. Now, further, so what is a simplicity complex? A simplicity complex is a collection of simplices such that K contains a simplex, and then K also contains every face of a simplex. Every face of simplex. Okay, so if two simplicials in K intersect, then their intersection is a face of each simplex. Okay, so that is a formal definition of a simplicial complex. Okay, so for example, let's take this. This is a simplicial complex. All we put together, it's a simplicial complex. Okay, so the simplicial complex is a collection of two simplex. We have two simplex here, P0, P1, P2. And then we have a collection of all the edges. Yeah, all the edges, which is one simplex. This is two simplex. Okay, I just write two simplex. These are all one simplex. And this is zero simplex, all the points. So all the points will be zero simplex. All the edges, all the edges here, yeah, all the edges would be one simplex. And then we have here 1, 2 simplex. So this is a simplicial complex. Right? You see, let's take this triangle here, P0, P1, P2. Right? So the P0, P1, P2. If we have a 1, 2 simplex, or of course, this 1, 2 simplex consists of edges, which is P0, P1, P0, P1, and then P1, P2, and then P2, P0. So you see, so if we have two simplex, definitely we will have one simplex, which is the building block for two simplex, right? Of course, and then if we have this so-called edges, for example, if we take this edge, it consists of two zero simplex, P0 and P1. So that's what it means here, right? So the face here, yeah, the face, for example, the two simplex, the face is actually, you can see the area which is in gray, right? So for one simplex, the face is actually the edge itself. Of course, for zero simplex, there is no face. So that is what the meaning of this simplicial complex. All right. Okay. Right. So now counting. Right. So as you saw earlier, the way to count after we construct simplicial complex is pretty much straightforward. Right. For example, at this resolution, we have how many connected components? One huge connected component, second connected component, third and fourth and fifth. So beta 0 is 5. All right, okay. Next, now let's compute beta 1. How many holes do we have in this simplicial complex at this stage? How many? We have 1, 2, 3, 4. We have 4 holes. Do we have Betty 2? We don't have Betty 2 actually. Yeah, this is actually a two-dimensional space data set. So there is no tetrahedron. In three-dimensional data set, there are chances to create tetrahedron, but currently there is none actually. Okay, all the gray space, the gray filled triangles are basically two simplex. Okay, so Betty2 is 0. So what is Euler characteristic for this simple complex? It will be 5 minus 4 plus 0, which is 1. Yeah, so this is the information, shapes information in the context of Betty and also Euler characteristic. Okay, right. Uh, so again, I give how to compute directly Euler characteristic um, from simple cell complex. So for one way is, of course, we compute from Betty number. Yeah, so we look at the Betty number for this simple cell complex. We can directly compute. So Betty 0 is 1, yeah, and Betty 1 is 1. There's one whole, and there's no Betty 2. So we can just like alternate sum of it. We get 0. Another way of doing it is we compute number of simple cell complex. For example, 0 simplex. How many are there? 0 simplex is basically points. We have 4 points. And then 1 simplex is the edges. How many edges are there? 5 edges. And then how many face area? Yeah, covered area, 2 simplex. How many 2 simplex are there? 1, 2 simplex here. So we can also do the alternating sum, which is the building block of the simple cell complex. We would get the Euler characteristic as well. So there are actually 2 ways to compute Euler characteristic from a given simple cell complex. Okay, right. So we are now ready. So next thing is now, you see, given a point, given a collection of point, which is your point cloud, from point cloud we are going to create simple cell complex. When we create simple cell complex, so when I'm going to connect 2 points, when I'm going to create the face, the triangle, the 2 simplex, when I'm going to create 1 simplex, when I'm going to create two simplex from given point cloud. So that, yeah, to answer that, we can create different kind of condition. We can give different kind of condition to create. For example, when let me give a ball. Yeah, this ball is basically with radius r. Yeah, for each point they get a ball with radius r, let's say. So I increase the size of the ball. As I increase the size of the ball, when the size of the ball intersects, for example, and then I create one edge. So this edge is created, this edge is created. This two does not get edge yet because the ball is yet to intersect. At some point, okay, this ball actually now intersecting. 2 balls are intersecting, so we get, this is now 3, 1, 3, 1 simplex. Yeah, there are 1 edge, 2 edge, 3 edge. So 1 simplex is called an edge, right? So there are 3, 1 simplex or 3, 1 simplices in plural. Okay. So when 3 points intersect, as you can see now, there's still hole, which means this simplicial complex still indicating there's a hole. Let me delete and show you. Yeah. So they're actually intersecting, you can see, but there's still hole here. There's the simplicial complex, which is now in this form. So there's actually a hole, which means simplicial complex really showcasing what's happening based on the overlap of the ball, right? Still there's a hole, so okay, great. And then after the 3 balls intersect, the hole is now closed. Okay, there's no more hole, so we get 1, 2 simplex. Yeah. 1, 2 simplex. Okay, so it's actually a nested, right? It's nested from radius. Let's say we usually start from radius equals to 0. We can go to radius into for some value here. Let's say r star, and then from r star onwards, of course, we increase to until plus infinity. It's not going to change, right? Because all 3 has been connected already. So it's going to stay as 2 simplex forever. All right. So this process From r equals to 0, as I increase to r is to equals to plus infinity, it's called filtration. Filtration. Yeah, filtration of simple complex simply means we are constructing a collection of simple complex from R0 until R infinity. So we get a many collection of simple complex. Of course, the previous simple complex was when R is equal to 0, everybody by themselves. As I keep on increasing, so I have, for example, at this point here, I have a simple complex denoted with K subscript 0, and then here K subscript 1, K subscript 2, and K subscript 3, and so on. I can keep on increasing. This is called the nested sequence of sub-simple cell complex for a given filtration. The filtration that we did is based on radius R. Okay, all right. So let's look at a demo. Let's look at a demo. Okay, so we have a collection of points. As you can see, I'm going to increase the size of the ball. The ball is actually called a cover. If you still remember, we had cover for mapper algorithm also. So I keep on increasing. There are overlaps. Meaning there are overlaps between balls. We're going to we create an edge, one simplex. So when 3 balls overlap, we create two simplex. Yeah, as you can see. So we can just keep on increasing the size of the ball until everybody intersect among each other, then it becomes just one connected component. And currently there are, each one is one component. As I increase, when they join, of course, the connected component decreases. Connected component decreases. Now I have only one connected component, right? Let's see, as I increase, okay, and this, and this, and this, okay, at this with radius, at this radius, I have two Betty one hole in here, and the other one, it's a big huge hole here. So I increase, the small hole died, the big hole still is living, still persisting. The hole is still persisting, the big hole is still persisting. As I increase the radius, the big hole is still persisting. At some point, yeah, it dies. At some point, it dies, the hole is closed. So there's a birth of the hole and the death of the hole, right? So we can keep track of all this information, and this information will be then later um, represented in the form of persistence diagram. Yeah, birth of a hole, death of a hole, birth of a connected component, and then death of connected component, which means the component get joined with another, right? Okay. So the process of persistent homology, actually 3 steps. So previously you saw for map algorithm, there are actually 4 steps. Here, only 3 steps actually. First is geometric realization. Second is algebraic topology. Finally, representation theory. So first is under geometric realization, as you can guess, we are basically going to create simplicial complex at different resolutions. So previously I said R, actually we are using alpha representing the radius ball. Okay, the radius ball. So we're going to start ball with equals to a radius equals to 0, and then we're going to just keep increasing until everybody gets connected. Right. So when we do this, right, when we increase the ball, we will keep track of the birth and death of all the components, the Betty 0 and Betty 1. So basically, the birth and death can be represented in the form of a boundary matrix. It's called a boundary matrix. So boundary matrix, we get a matrix, nice matrix called boundary matrix. From this boundary matrix, you can row reduce the matrix, just like we do like Gaussian elimination, such a way that you can compute the Betty numbers. Yeah, Betty numbers. So H0 is homology class which represents Betty 0. H1, the homology class 1, the rank of homology class 1 is actually Betty 1. The rank of homology class 0 would be Betty 0, and so on and so forth. So what happened is that representing the information in the form of matrix, then we use linear algebra to solve it. So that is why we call it as algebraic topology. The topology information being row reduced, the matrix being row reduced, the topology information is represented in the matrix being row reduced using linear algebra. And then once you have the birth and death, and then the homology birth and death, you would be able to then represent it in the form of a persistence diagram or a barcode. It's just a visual representation of the birth and death here. Yeah. Okay. So those are three steps actually, right? Those are the three steps. All right. As the change of radius, keep track of the changes happening in the simple scene complex. Represent it in the form of matrix, boundary matrix, row reduced boundary matrix, and compute. We can try to directly compute Betty numbers, or we just keep track of birth and death values, BI and DI, birth and death values of some homology class, Betty, maybe Betty I, any Betty, Betty 8, Betty 1, Betty 0, and then use this information, represent it in the form of persistence diagram or barcode. Okay, so I'll show an example of it. So how to do it? Of course, we will not do by hand. Yeah, we will not do by hand. It's not easy to keep track, to represent it in the form of a linear algebra, which is boundary matrix, and then get the persistence diagram barcode. Rather, we can use many packages. The famous ones would be GUTI package or Giotto TDA package, yeah, Scikit TDA package. These are main three packages available out there for free where we will be using it. Okay. Now, let me show an example. This is actually, this is a PDF file. If you open with the Adobe, you would be able, Adobe PDF Reader, you'll be able to play it and see the visualization. So let me show. Okay. So this is, okay. So when you press play, you can see the increased size of the ball on the left-hand side. So alpha represents the radius of the ball. On the right-hand side, you can see the birth and death of topological feature. H0 represents connected component. As you can see, all the points. So each point has birth and death. The birth, the appearance of that connected component. The death, which means the component that one point is getting connected to another point. So the death of the connected component. So that is connected component. Whereas for a Betty one, you can see the birth of the small hole first at some value like 8 point, about 8 point something, 8.9 maybe. So we get to see one hole here, small hole. That's the birth of here, this hole here. So yeah, yet to die. Just give birth now. As I play at this point. Yeah, at this point, 1.4. Yeah, 1.4, radius 1.1, that's the depth of the second hole. All right. And the depth of the first hole. The second hole, they appeared about 1 plus. It is yet to die. Okay. Let's do it probably a bit. Let me play. Oops. At 2.2, the depth of the second hole. So you can see the hole, which is the point which is far away from the diagonal line, are the prominent holes. Whereas if it is very near, the holes are not so prominent. Okay. Okay. The ones that are very near to the diagonal line are those birth and death, like very small, very fast. Just appeared and then died quickly. So these are the information. These are the information which we can now make it as a vector and use it for machine learning. Okay. Okay. So let's play. Play it and then have a look at it. Okay, so from point cloud, we do persistence diagram. We do persistent homology. We get persistence diagram. So each point here is actually a two tuple. Yeah, it has got a birth value and death value, birth and value and death value. Okay, so what happened? Okay, we did filtration. The first thing is we did filtration with radius. For this is like a radius 0 until we increase the radius until the radius equals to infinity, right? So from this sequence, yeah, we can get actually the boundary matrix. Yeah, the homology class, we can actually get a boundary matrix. From this boundary matrix, we can row reduce, we can get birth and death of all the features, topological and geometrical features. So these are the birth and death. D represents either D equals to 0 means connected component, D equals to 1 means Betty is representing Betty for Betty 1 and so on and so forth. Okay, we get a collection of multi-set, actually, collection of, it's called a multi-set. So persistent homology, yeah, it takes the filtered space. Yeah, we have this filtered space and then returns a persistence diagram. Yeah, the persistence diagram in the form of B and D. So of course the output, the persistence diagram output is actually in R2. Okay, all right. Now from this, we can actually directly use this for machine learning, but we would actually vectorize it. An example of a vector, we can use a lifespan. A lifespan is di minus bi. So there's a lifespan, right? So you know from from this diagram, the long lifespan. This is like very long lifespan. This is very short lifespan. This is even very small, short, very short lifespan. The long lifespan, prominent topological feature. Very short lifespan, not so prominent. Okay, that's the first second part here, right? And then we are going to do vectorization. So let's assume I calculate for all lifespan. So I can calculate all the lifespan here, right? So calculate all the lifespan I can calculate. I can directly use for actually machine learning. But let's see a proper way of doing making a vector out of this for machine learning. One way is to do a persistence landscape. Yeah, persistent landscape was first introduced by Bubenik, a professor. He's in University of Florida. Okay, but how he did it. All right, how he did it. Okay, let's see. Let me just show you with the diagram how he did it. So first, what he did, he draw a tent function. Like this, this is a tent camp, right? You do camping. So you have 3 points actually. This is how you do it. This is a camp. So we do a tent function. So tent function is just a linear function. Yeah, so you just do like that. For each, construct a tent function for each pair, and then you rotate 45 degrees. When you rotate 45 degrees, this is what you get, right? So once you get this now, so every single point here, we have points actually, every single point. This is actually now a vector, okay? So now, in order to differentiate all these vectors, we give the first layer, the first highest layer of the points. You see the first highest layer? We call it, this is lambda 1. And then we have a second layer now, second highest layer. Okay, this is the second highest layer. We call it as lambda 2. And then finally we have the last layer. Here, oops, should color it differently, lambda 3. You see? So lambda 1, I can make the resolution, I can parameterize it 0 to 100. So at 0, this is the value. At 1, this is the value. At 2, this is value. I can do 100. Same thing for lambda 2 also. I can map it to 0 to 100. So I get each corresponding values, the y values. Okay. So I keep all the y values. So lambda 1, I have 0, the value of y until, which is from 0 to, let's say, 1 to 100. Then lambda 2 also 1 to 100. Lambda 3 also 1 to 100. So this is actually, for example, I can make it lambda 1, lambda 2, lambda 3. I get 1 to 300. Yeah, I do a lambda 1, lambda 2, lambda 3. So I have 1 to 300. So this is now a feature. So rather using a point cloud, this is the feature to which represent my data, right? So I can use this for classification now. Okay, so this is how I do it. Okay, the mathematics here, not to worry. The first part is drawing a tent function and just plotting it using a new space. Yeah, this is a new space now. The new space, as you can see, it involves the birth and death of the set. Okay, all right. So this is the landscape. So it's called persistence landscape. From persistence diagram, we get persistence landscape. So we can use persistence landscape to do machine learning. We can also make an image out of it, persistence image. For example, of course, the rotation, after doing the rotation, the point here still stays as it is, right? So now at each point here, we give the Gaussian value. Yeah, the Gaussian is like that, right? So at peak, it gets high value, surrounding it gets low value. At peak, so this is at peak, it gets very high value, surrounding it just get low value. Maybe at peak it gets 1, surrounding it gets like maybe like 0.5 and then 0 everywhere. So we can give a Gaussian value at each point, and then for example at this point here there are 2 points actually, 2 points overlapping each other. That's why the addition of Gaussian value, the summation of Gaussian value, you get very higher, right? So this is a persistent image. So you know the vector here, all right? The vector for persistent landscape, it's based on layer, right? Layer 1, layer 2, layer 3. We can put together and create one long vector, which would be the feature vector. But persistent image, you know, the image is made out of pixels. These are all pixels. The one, let's say this is 1 to 100. Next is, of course, second row 1 to 100 also. So we will use the feature vector here as well. So the feature vector here, we will flatten this persistent image 1 to 100. The one is this here. 100 is this one here. And then this one is 1 again to 100 till here, corresponding point. And then next, right? So 1 to 100. You do a long vector. Yeah, very long vector. So this is 100 by 100. You can imagine 100 by 100. That will be the length of our vector. So this will be our feature vector for machine learning. So what we did is that from persistent diagram, make persistent image. It's called vectorization. From persistent diagram, we did persistent landscape called vectorization landscape. Then we use straight away the feature. Here, taking the persistent image, we have to flatten it. Use numpy flatten function, flatten it, make a long vector, and then we push it into machine learning. Okay, so these are 2 examples of vectorization of persistence diagram. Okay, this is an example of work. Okay, imagine now, actually from this is a dynamical system, equation of a dynamical system. This dynamical system will produce point cloud in 2-dimensional space. This is an example of point cloud 2-dimensional space, and it has a so-called parameter R. And this parameter R, based on the value, it can create different kind of point or dynamics. Yeah, for example, when R is to 4.3, that's got some sort of a small 2 holes you can see, right? So for R equals 2.3, this is the persistent diagram you get. So you can clearly see like, oh, there are actually 2 prominent holes. There are somewhere there's 1 small hole also. So if you were to convert, vectorize this persistent diagram, you get persistent landscape. This is actually persistent landscape, typo there, okay? Persistent landscape. Similarly, when R is 2.3, this is how the persistent landscape looks like. When R is 3.5, this is how the persistent landscape look like. R 4.0, R 4.3, R 4.1, and R 4.3. R 4.3 we just saw, right? So we can clearly see persistence landscape can really capture the information of the shape from this point cloud, and then we can straight away use this vectors, lambda 1, lambda 2, lambda 3 vector, which is landscape, persistent landscape, for classification rather than using the point itself. Okay, so how we can do it? So the example that we will look at in our lab would be, we will create 10 point cloud for each. For class, we call it class 0. So when R is 2.5, we create 10 point cloud. So we do for until R 4.3, we call it class 4. So we have 5 classes: class 0, class 1, class 2, class 3, class 4, 5 classes. So for each class, we do 10 point clouds. And then for each, so we have 50 point clouds altogether. And then we draw persistence diagram for each. Then what we will do, and then of course we are going to shuffle it. We're going to mix them together, and then we're going to split it. Test 10 point cloud, and then train 10 point cloud. So rather than saying point cloud here, I've already converted into persistence diagram, right? So 10 persistence diagram, of course, it's with this label R, type of R, and then 40 for training. So if you still remember, for TDA, for pushing it to, the next thing is that we are going to push into grid search CV. Yeah, grid search CV. So it's actually cross validation, right? Grid search CV such a way that it will propose me, find me the best model, right? So for H0 and H1, there will be you will see that there's like plus infinity, right? So since we do like R infinity, things won't be not going to be changed. We would want, you don't want to that point. We will remove that point, the infinity point, and then we can also normalize. So normalize means what? So the value is going to be between 0 to 1 or 81 to 1. It's up to you how you want to set it. And then we're going to use a persistent landscape, and each lambda is going to be 100. Each lambda, for example, just now I showed you lambda 1, so it's going to be 1 to 100. So maybe I want to use first 5 lambdas. I can do that, which means first 5 layers. And then I'm going to use an estimator or a classifier, random forest classifier. And then after setting all this, I'm going to push into grid search CV. It's going to do hyperparameter tuning. It's going to propose me the best model. After I'm going to create the best model. Once I have the model, I'm going to test it. Yeah, to testing. So based on, you will see, we will be doing this in our lab. The training accuracy is very good. Trace accuracy is about 0.8. So not bad, right? Not bad. Okay, not bad. So we can now use this for a given new data set. You can use this model. You can do same thing, convert to the persistent diagram, convert to, after doing persistent diagram, new data, we get PD after getting persistent diagram, and then we do a persistent landscape. Using the persistent landscape, push into the model, and then the model will give me the class, the type of class that this data set is. Okay, this is an example of classification problem using persistent homology. So the takeaway is, of course, TD is a semi-supervised technique. You have learned two types. Yeah, two types. One is mapper, and the other one is persistent homology. So for mapper, if you still remember, yeah, mapper, so it is a type of EDA, exploratory data analysis. And of course, you need to find the right lens, yeah, the right lens, or I call it a filter function, yeah, filter function. This filter function should be able to differentiate between the points such a way that it can show me, illustrate me the structure of the points, how they are connected. The next thing is persistent homology. The persistent homology, what it does is that it's actually capturing a lot of information. Yeah, so the global topology is the information that you see all the holes and the connected components. In fact, it is also catching local geometry, which is, for example, the curvature, how curvy is the shape. It's also capturing actually. Right, all those points very near to the diagonal line, actually capturing how the data is being connected over the radius r, which can encode the local geometry of the information, which means when you use precision diagram as it is for your machine learning task, you are using both information, geometry information, topology information of the data to do machine learning tasks. Right. So what we did is that we used PH to feature engineer. Okay, what we engineer is the shape information, and then use as shape information just like our thumbprint to differentiate, to do classification for this problem. So with that, so thank you very much. There are many books out there. So in fact, I've ordered and now the books are available in library as well. Right. So wish you best. You can now do your project. Thank you.